closely looking at the stars and making some measurements and thinking about it, we can actually measure the mass of stars, and we can ask, we're almost ready to start modeling, we need to know, where do the masses of stars along the main sequence line up with their masses? And so we can add masses into our plot for the main sequence, and here's what we learn. Masses don't vary very much. Way down here, down where the red dwarfs reside, masses of stars we discover are as small as 1/10 of a solar mass, but not much smaller than that. And the biggest, most luminous, hottest main sequence stars top out at 50 solar masses. We rarely find anything even up there. And so by measuring a few stars along the main sequence, we can figure out comparison of the mass of a point along the main sequence. The main story is that the heaviest mass stars are the hottest and the most luminous. And now we can fit it into the model. Because when you go and model a star, basically, if you say that a star is a ball of hydrogen, I don't need to tell a good modeler the luminosity or the radius. I would tell him, take a ball of hydrogen, held up in hydrostatic equilibrium against its gravitational attraction by hydrogen fusion, and then run your equation. Now, in practice, that's a little bit difficult, but in principle, nature knows how to do that. So if you give nature a ball of hydrogen of a given mass, it'll produce a star, and that star will lie somewhere along the main sequence, and we can now attempt to study modeling. We'll discuss the results of that in our next clip. But first, let's note that there's a very reasonable approximation. You can do better, but the luminosity along the main sequence scales with mass. As I said, the heavier stars are more luminous, and it scales like the 3.5, or 4th power of mass. It's not exactly fixed relation. You can improve this and go into the details, but this is good enough. What this means is that a star that is twice as massive as the sun has a luminosity between 8 and 16 times the luminosity of the sun, is way more luminous. This is how change from 1/10 of a solar mass to 10 solar masses gives us this 5 orders of magnitude or 7 orders of magnitude change in luminosity. Now this sort of makes sense, and our models bear this out. A heavier star has more pressure from the outer layers crushing down on its core. The pressure in the center is higher. Densities in the center are higher. We said that fusion proceeds best at high temperatures and densities, and that means the rate of fusion in a big star will be higher. That's the way that mass is going to determine the rate of fusion, and so it makes sense that bigger stars will be more luminous. But note that if, say, the core of a star like the sun, we said that the sun, we estimated the age of the sun, how long the sun would last, by saying if it converted all of its hydrogen to helium, it would last 100 billion years, but the sun will actually stop converting hydrogen to helium when it has converted 1/10 of its hydrogen, because that's the amount that will be available in the core. If all stars had about 1/10 of their hydrogen available in the core, what this would tell us is that big stars run out of hydrogen much faster than slow stars, and indeed appended to this table of the main sequence is a list of main sequence lifetimes adjusted. Remember, right over here, the sun has a main sequence lifetime of about 10 billion years, and stars with luminosity 10 times that of the sun, it turns out, only last 1 billion years. And up here, the really bright type O and B stars might last only 10 or a few million years, and the lightest red dwarfs last hundreds of billions of years. What that tells us is that if we see a type O main sequence star, since they only live 2, 3, 5, 10 million years, that star is brand new. When the sun was formed 5 billion years ago, that star was nowhere near to existing. So when we see, say in Orion's belt, type O stars, we know that very recently stars have been forming there, just by looking at the scaling of the masses and the luminosities. And we'll see what modeling tells us and conclude the week in the last slide of the week, last clip of the week now.